Excuse me, please. Where is my...
You can probably press Ctrl L to make it full screen.
Dear colleagues, I am very pleased to welcome you to such a representative forum. My report is devoted to a new direction in our research, namely the theory of positive degenerate semigroups of operators. I will tell you results only for positive degenerate holomorphic semigroups of operators. As a new results will be reported by my young colleague in the next report. Let me begin my report. First, we consider the linear let Gotti Q and F be real Banach spaces. The operator L is linear and continuous operator, and M is linear, closed, and densely defined operator. Let us consider the non-homogeneous linear Sobolev type equation. One. For the first time in history, the term Sobolev type equations appeared in the paper one. The other of this term is the Rolf-Walter. Currently, this equation occupies a very vast array among classical equations of mathematical physics and are studied in very different aspects. See, for example, 4 and 3. Besides that, there are many treatises in which Sobolev type equations have other names. For instance, degenerate equation in 4 or partial differential equations and systems not solvable with respect to the highest order derivative, 5. In this report, the term 4 and 5 are considered to be synonyms for the term 1 of 3. We're interested in the condition under which equation 1 has a unique positive solution. The main tool to find such a condition is the theory of positive degenerate holomorphic semigroups of operators. First, we consider the linear homogeneous Sobolev type equations. Under certain condition on the operators L and M, there exists a degenerate holomorphic semigroup of operators, which is resolving semigroup of equation 2. This semigroup has a phase space big Gothic U P1, so that for any element small u sub 0 from this phase space, there is a unique solution to the Cauchy problem, which also lies in phase space pointwise. Let us suppose, in addition, that Gothic big U sub plus is the proper generative cone, and all Banach space is the Banach lattice. If initial element belongs to this intersection, then the solution to the Cauchy problem will be a positive solution to the equation 2. To obtain a positive solution to equation 1, we must consider the Showalter-Sidorov condition instead of the Cauchy condition. However, in this case, the positivity of the semigroup is not sufficient, and we need the Banach lattices should be matched. Further, we use the abstract results in order to construct a positive solution to Showalter-Sidorov problem 4 for an interpretation of abstract equation 1, where the operator is the matrix, diagonal matrix, such that L sub k and M sub k are polynomials with real coefficients such that finally, I know that all the results of the report were published in the article below. Let us construct the generate positive holomorphic semigroups of operators. Suppose that Gothic B, Q, and F are Banach spaces. The operators L is linear continuous and M linear closed and densely defined. The foundation of our research is the theory of the generate semigroups of operators and the phase space method described in Treatise 2, Chapter 3. Let us give the necessary information on the theory of degenerate semigroups of operators in Banach spaces. Consider L resolvent set and L spectrum of the operator M, as well as the operator function which is called the right L resolvent of the operator M. The operator functions are called the right and left L resolvent of the operator M respectively. Definition 1. The operator M is called P sectorial with respect to operator L with the number P, in short LP sectorial, if this condition are satisfying. Lemma 1. Let the operator M be LP sectorial for some P, then there exist two degenerate holomorphic semigroup of operators. Since the semigroup, such semigroup are holomorphic, we set kernel of the first semigroup and kernel of the second semigroup. Let L sub 0 be the restriction of the operator L to such subspace. It is kernel of semigroup of the first semigroup. And M be the restriction of the operator M on this kernel. Theorem 1. Let the operator M be a sectorial for some P. Then the actions of operator L and M sub 0 are splitting, and operator is nilpotent is of degree less than or equal to P. Definition 2. The operator M is called strongly LP sectorial on the right or on the left for some P if M LP sectorial for some P and such conditions are fulfilled. Theorem 2. Let the operator M be LP sectorial on the right or on the left for some P, then there is the projector P and the projector Q. Both projectors are the strong planes of corresponding semigroups. It is easy to see under the condition of theorem 2 there exists a splitting of space U and F. Definition 3. The operator M is called strongly LP sectorial for some P. If M is strongly LP sectorial on left for the some P and such condition is fulfilled. If V is the degenerate holomorphic semigroup of operators, we can define image of this semigroup and image of this semigroup. Theorem 2. Let the operator M be strong LP sectorials for some P. Then there exists the inverse operator and operators L. Operators L. And there exist operators S and T, such that the semigroups have the next form. Let us describe the condition under which these semigroups are positive. Definition 4. The real Banach space is called the ordered Banach space if if there exists the order relation which satisfies the axioms of reflexivity, transivity, antisymmetry, and is consistent with the vector structure of the space B. If such conditions are fulfilled, if in addition the order relation is consistent with the metric structure of the space B, it is for all X there exists such element, then the ordered Banach space is called Banach lattice. Definition 5. Let B a Banach space, a convex set such that is called a cone. A cone is called proper if and generative if that. Let B Banach lattice. Then easy to see B as a proper generative cone. On the other hand, let B Banach space and C proper generative cone. Let us introduce the order relation by the formula. Further, well distinguish the ordered Banach space and the Banach lattice. Definition. Let B Banach lattice. The operator is called positive if if the image of operator S contains in B sub plus a semigroup of operators is called positive if the same relation are fulfilled. Theorem 4. Let operator M be stronger LP sectorial for some P and the Banach space be a Banach lattice. Then the following statement are coherent. The operator is positive for all sufficient large. The generate holomorphic semigroup is positive. As an let B now consider a linear let уже сказал. Now consider linear and unhomogeneous Sobolev type equation 1. The vector function is called the solution of equation 1 if the function satisfies the equation for some tau in R sub plus and F image of such interval in F. The solution to equation is called the solution to problem 1.3 or problem 1.4. If the solution satisfies condition 3, condition 4 for some element of U. Definition 7. Let the operator be strongly LP sectorial for some P. The Banach lattice U and F are called concordant with respect to the PLM, briefly LM concord, if such condition are fulfilled. Let the operator be strongly LP sectorial for some P. The Banach lattice is U and F BLM concordant, and the generate holomorphic semigroup of operators would be positive. Then for any vector function such that and F sub super 1 and for any vector there is a unique positive solution to problem 1.4 and this solution has the form. If in addition the initial vector satisfies condition condition 6, there exists a unique positive solution to problem 1.3 and the solution has a form 5.
Дальше. 13.
Consider the monotonically increasing sequences such that limit is equal to infinity. Construct Sobolev spaces of sequences which are Banach spaces endowed with the norm. Let operator L at M has such form. Simply be polynomials of degrees R and SK respectively with real coefficients that such that the roots of the finite number of the polynomials are the number construct the operator L and M acting in Banach spaces of sequences satisfying the condition. Suppose that there exists S maximum and R maximum, and construct the operator L and M. By virtue of condition 7, we obtain that S greater than R set then the apparatus theorem 6. Suppose that condition 7 is satisfying and the polynomials L and M for all K have only real roots and don't have common roots. Borrow the roots of point number of the polynomials are the number and the condition 8 is satisfied. Then the operator M is L null sectorial. Construct the splitting of the space U into the direct sum of two subspace. The first subspace is the kernel of the operator L, and similarly construct the splitting of the space F into the direct sum of two subspace F super 0 and F super 1. Then the operator L sub 1 has such form, L sub 1 super minus 1 have the such form, and operator M sub 0 super minus 1 has the such form. In the space, you consider the family of vectors, and the canonical cone formed as a closure of linear combination of the vectors with non-negative coefficients. Then the space forms a Banach lattice. Similarly, the space F, we consider the family of vectors as a canonical cone F as the closure of linear combination of such vectors with non-negative coefficients. Then the space form a Banach lattice. Here sets are the follows. The cone such that and the cone such that. Therefore, it follows from the construction of operators L sub 1, L sub 0, L sub 1 super minus 1, that the Banach lattice are LM concordant. Theorem 7. Suppose that the conditions of theorem 6 are satisfied. The values of polynomials L, K, and M, K are positive for such that L, K is equal to 0. Then for any vector function such that and for any element U of U such that there exists the unit positive solution to problem 1-4. It is the Schroeder problem to the equation 1. And the solution can be represented as such formula, where where semigroup is has the form. Thank you for your attention. That's all.
Right. Thank you very much. Are there any questions, comments?
Muy.
Anyone? Actually, I have a couple of questions, but I will probably send them to your email. Rather technical. Okay, so if there aren't any questions, let's thank the speaker again.